And welcome back, students. Today we're going to be continuing our discussion on optimization by discussing trade-offs and bottlenecks. All right, let's talk a little bit about the weakness of optimization. In some cases, optimization relies on using more elaborate algorithms, making use of special cases and special tricks, and performing complex trade-offs. A quote-unquote fully optimized program might be more difficult to comprehend and hence may contain more faults than an unoptimized version. Beyond eliminating obvious anti-patterns, some code-level optimizations also decrease maintainability, so it's harder to maintain your code if you need to do fixes or you have bugs you have to track down. So it can actually make it harder by optimizing it to fix your code. Let's discuss those trade-offs. Optimization will generally focus on improving just one or two aspects of performance. Things like execution time, memory usage, disk space, bandwidth, power consumption, or some other resource. This usually will require a trade-off, where one factor is optimized at the expense of another. For example, increasing the size of the cache improves runtime performance, but it will also increase the memory consumption. Other common trade-offs include things like code clarity and conciseness. So you might want to make your code more clear, or you might want to try and condense it down. Balancing the optimization is the key here. There's instances when the programmer performing the optimization must decide to make the software better for some operations, but at the cost of making other operations less efficient. These trade-offs may sometimes be of a non-technical nature, such as when a competitor has published a benchmark result that must be beaten in order to improve commercial success, but comes perhaps with the burden of making normal users of the software less efficient. And you see a lot of benchmarking stuff go on, especially when you look at things like hardware developers for like things like CPUs, GPUs. They do a lot of benchmark testing, so you'll see a lot of stuff that goes on here. And it's really the optimization test. The software may not necessarily be as efficient, which is one of the things that you have to look at. All right, let's discuss those bottlenecks. Optimization may include finding a bottleneck in a system or a component that is the limiting factor on performance. In terms of code, this will often be a critical part of the code that is the primary consumer of the needed resource. Although it can be another factor, such as things like input-output latency or network bandwidth. Because remember, there's a certain number of cycles and stuff that is needed for the processor to be able to handle all that information. In computer science, generally the rule is about 80% of your resources should be performing only about 20% of your operations. So that means the other 20% is handling the other things. So 20% of your system resources are handling 20% of the operations. All right, let's discuss those algorithms because we talked about them quite a lot in this section. More complex algorithms and data structures perform well with many items, while simple algorithms are more suitable to small amounts of data. Makes sense. More complex, more data, smaller, less data. The setup, initialization time, and constant factors of the more complex algorithm, though, can outweigh the benefits. And thus you might have a hybrid algorithm or an adaptive algorithm, which may be faster than any single algorithm. So you will often see is not just simply one algorithm trying to handle every single system, but you'll have multiple algorithms working together. In some cases, one of the tricks you can do are things like adding more memory or allocating it to help a program run faster. For example, a filtering program will commonly read each line and filter and output that line immediately. This only uses enough memory for one line, but performance is typically poor due to the latency of each disk read. Performance can greatly be improved by reading the entire file, then writing the filtered result, although this uses less memory. Caching the result is similarly effective, though also requiring a larger memory use. And that concludes our notes, folks. Until next time.